Hi, welcome to this particular module. In this module we will look at silicon dioxide. In the last module, if you recall, we have seen silicon process to develop or fabricate a silicon wafer. Then we have seen what is the importance of silicon in IC industry, right, and we also saw Miller indices that will help to understand the orientation of the silicon wafer. Now let us understand what is silicon dioxide and the importance of silicon dioxide not only in the sensor fabrication, but also in the electronic industry is vast and it is very important. Okay. So, if I show you the screen, what you can see is that depending on the thickness of oxide, the application becomes different. So, let us start from the minimum, which is 1 nanometer, right. So, whenever you take a silicon wafer and the silicon wafer is in contact with the environment, then it will develop a thin layer of silicon dioxide. When it is contact with the environment, it develops a thin layer of silicon dioxide. So, this silicon dioxide is not useful, we do not require it. Okay. And to remove this silicon dioxide, we say, instead of removing, the technical term is etching. To etch silicon dioxide from the silicon, which is your native oxide. This is called native oxide because we have not done any particular process to form the silicon dioxide. It is formed on silicon because silicon wafer is in contact with the environment, and since our environment consists of oxygen, it will react with silicon to form silicon dioxide, and this silicon dioxide is not useful. So, we have to etch silicon dioxide. For etching silicon dioxide, we will use a chemical called buffer hydrofluoric acid, BHF, right. So, if you dip the silicon wafer, this wafer if you dip in BHF, then what will happen? You will see that the native silicon or native oxide that was grown on silicon wafer will get etched, alright. So, this is the native oxide is close to 1 nanometer, alright. Now, that is about the native oxide. Now, let us understand the gate oxide. So, those who are from the electronics background, you will know a little bit about MOSFET, right, and if you know about MOSFET, there is a source, drain and gate, source, drain and gate, right. This can be metal again, this is contact for source, contact for drain, right, and this oxide is your thin layer of SiO2, which is also called gate oxide, which is called gate oxide. What is the use of this oxide? You see, if you have a n channel silicon wafer and you want to let us say P type silicon wafer, and you want to have the channel form between source and drain, then what you will do? You will make gate negative, right. You will make gate negative with respect to the source and drain. So, what will happen? If negative is there, then holes will be attracted. Is that what you want? You want holes to be attracted? No. So, you have to make gate positive with respect to source. Now, if you make positive, then what happens? The minority carriers in the P type silicon wafer will be attracted towards gate, and form this particular channel between source and drain, right. So, when you make gate positive with respect to source and drain, the minority carriers in the silicon wafer, which is P type silicon wafer, which are electrons, will be attracted towards gate and forms a channel. So, what happens if there is a formation of channel? You can see that this channel is conductive, this gate is also conductive, and in between there is a silicon dioxide, right, which is this one, which is an insulating material. That means you have two conducting plates separated by a insulating material, and that becomes your capacitor, that becomes your capacitor. So, anyway, that is details about how the MOSFET will work. We are not going into that details right now. Our understanding is what is the role of this oxide. So, the role of this silicon dioxide, if it is between 1 and 10 nanometer, you can use as a gate oxide, you can use as gate oxide, which is this one. Now, let us see masking oxide. What is masking oxide? So, let us take an example of masking oxide. I have a silicon wafer, okay, silicon wafer. Now, what I want is I want to create a pit in silicon wafer like this, okay. So, the way to etch silicon wafer is by two technique. One is called dry etching, another is called wet etching. Wet etching, again two, we have potassium hydroxide and we have tetramethyl ammonium hydroxide, right. Well, dry has RI, which is reactive ion etching, and DRI, which is deep reactive ion etching, okay. So, either we go for wet etching or we go for dry etching, so that we can create a pit. Now, to create this pit, if I dip this silicon wafer directly into etching a silicon etchant, what will happen? What will happen? The silicon wafer will get etched. Like if I dip this wafer in silicon etchant, the whole wafer will start etching. That means it will reduce the thickness of the silicon wafer will start reducing, right. Initially it was this much, after certain time when I dip this wafer, let us say in KOH, then silicon will get etched from this region, okay, which we do not want, because we want this design. So, for that we will deposit silicon dioxide on the silicon wafer, we will deposit silicon dioxide on silicon wafer like this, and this silicon dioxide can be 0.1 micron to 0.5 microns, okay. After depositing silicon dioxide, we will perform a process called lithography. Lithography. I will teach you lithography in the next module. Lithography using photo or photons is called photolithography, okay, photolithography. So, using the photolithography process, what we will do? We will protect silicon dioxide in this area. Do not worry about it how this has been done, just understand that there is a photoresist. PR stands for photoresist, I will teach you sometime, and we will remove the photoresist from this particular area. Now, if I dip this wafer in BHF, BHF stands for buffer hydrofluoric acid. Buffer hydrofluoric acid will etch silicon dioxide. So, if I dip this wafer in BHF, what will happen? My silicon dioxide will get etched. If I dip this wafer in BHF, silicon dioxide will get etched. Now, I will strip off the photoresist. I will strip the photoresist by dipping this wafer in acetone. Acetone is used for removing or stripping of photoresist. So, if I dip the wafer in acetone, what will happen? Photoresist will get stripped off, okay. After this, I can dip this wafer in potassium hydroxide. What will happen? Silicon will start etching, but silicon dioxide will not get affected. Why it will not get affected? Because KOH cannot etch silicon dioxide. So, if you see the screen, what you find is, if I dip the wafer in KOH, then I will get this kind of etching, right. What we want? We want the spit in silicon, right. So, after we get the required depth, all right, we will stop, we will take out the wafer from KOH, rinse it with DI water, dry it, and then dip this wafer in BHF. If I dip this wafer in BHF, what will happen? Silicon dioxide will get etched. And once silicon dioxide gets etched, we will get this pattern, we will get this pattern. But what happened, like what was the role of silicon dioxide here? The role of silicon dioxide, if you correctly understood, was to protect this particular area, right, or I should draw the arrow in opposite direction. You can see that silicon in this area is not affected when I dip this wafer in KOH. So, what was getting affected? Where the silicon dioxide was not there, this area, right, this area where the silicon dioxide was not there, it got etched. That means this silicon dioxide will act as a masking oxide, it will act as a mask through which the KOH will not penetrate, and the silicon dioxide will act as a mask for silicon wafer, it will act as a mask for silicon wafer. Okay. So, that is the role of masking oxide. And then comes a filled oxide. Filled oxide is when you want to use a thicker silicon dioxide, right, for generating the fills. Again we will discuss it at some point of time, if the time permits. We can also use the silicon dioxide as a filled oxide. So, the another role of the oxide is also in the back end insulators between metal layers. So, you have a metal layer, then you have to insulate some part of it, and you grow another metal, again insulate some part of it, grow another metal. So, you can do that on the back end side of the microelectronics chip, right, where you can use this insulator between two metals. So, having said that, for how this silicon dioxide is useful, we have seen few examples, right. But like I said, that if you have a silicon dioxide on silicon wafer and you dip in HF, which is hydrofluoric acid, then silicon dioxide will get etched and only silicon wafer will be left. So, in another way, if you want to see, then you have source and drain, right, source and drain. How the source and drain are created? The source and drain are created by doping impurities inside the silicon wafer. So, how to dope this source and drain inside silicon wafer? Again by using the SiO2. So, I have SiO2 here, then I have SiO2 here and here. Okay. How we pattern this? Using photolithography. We will see photolithography in the next module, okay, do not worry about it. So, these are silicon dioxide patterned on silicon wafer. Now, what I will do is, I will dope this silicon, because here SiO2 is not present, right, with let us say boron. If it is an N type silicon, I will dope this silicon with boron. So, what will happen? I will form source and drain. All right. So, in this case, when I am doping the silicon with boron, right, this boron doping will not get passed through, or the boron impurities will not get passed through silicon dioxide. Silicon dioxide will act as a mask for common dopants. And what are the common dopants? either they are N type dopant or they are P type dopant. It can be boron, gallium, phosphorus, arsenide, antimony, and a lot of other dopants are there, right. So, now the another very important point is that what is the temperature that is required for doping a particular impurity. So, if you see that if I want that diffusion time should be close to, let us say 10 hours, right, and if I draw a line like this, then and the temperature, and it is a phosphorus material and the temperature is about 1200 degree centigrade, then I require how much silicon dioxide? I require close to 1.5 micron silicon dioxide, or close to 2 micron silicon dioxide. However, if I want the same to happen at 1 hour, that means I want to diffuse the phosphorus at 1200 degree centigrade inside a silicon wafer for 1 hour, then what I get, what I want a silicon dioxide which is close to 0.8 micron thick, 0.8 micron thick. But in case of boron, if I want to diffuse boron into silicon, and again the time is 1 hour, then and the temperature is 1200 degree centigrade, then you can see here that you require of silicon dioxide which is close to 0.05 micron or 500 nanometer. Right. So, this chart or this table this plot helps us to understand what should be the thickness of silicon dioxide that can be used as a mask for the common dopants depending on the diffusion time and depending on the temperature for that particular dopant. All right. Let us go to the next slide. So, you can see here can also be used for mask against ion implantation. See, there are two techniques for diffusing the impurities. One is called diffusion and another is called ion implantation. Ion implantation. Okay. So, the SiO2 is not only used as a mask against diffusion, but can also be used for ion implantation while ion implanting the dopants into the silicon. Now, like I said, there are two different techniques for etching dry and wet. Same thing, there are two different techniques for growing the silicon dioxide on a silicon wafer. One is called dry oxidation and another is called wet oxidation. Let us see dry oxidation. See, silicon wafer at a high temperature when reacts with oxygen forms silicon dioxide, and if it is wet oxygen, then what we do, we have silicon wafer, we pass the water vapor on to the silicon wafer, the O2 reacts with silicon to form SiO2 and 2H2. 2H2 will be the gas that can come out from the furnace. All right. So, to do that, first is that the temperature required for both dry and wet oxidation is close or is in between 900 and 1200 degree centigrade. Okay, that is the temperature. And when you compare the reaction time or the growth time, then the wet oxidation is 10 times faster than dry oxidation. Okay. Another very important point is in dry oxidation, the film thickness is from 0.05 to 0.5 micron. It is an excellent insulator for gate oxides. That means, the one that I was showing you early, that when you have a MOSFET, you have a source, you have a drain, you have a silicon wafer, and you want to form a gate oxide on which you can again form the gate, right. This is your metal, this is your gate, again this is your metal, this is your metal for drain, for source. Then this particular oxide, which is your silicon dioxide, should be generally a dry oxide, because it will give an excellent insulating property when you are using silicon dioxide as a gate oxide. While for the wet oxide, we can have a thick but less than 2.5 micron. It is a good insulator for field masking or field oxide or masking oxides, but the quality of this oxide suffers due to the diffusion of hydrogen gas out of the film. You can see here this particular reaction, that you have Si plus 2H2O which reacts and forms SiO2 and 2H2. So, this when the hydrogen comes out or diffuses out of the film, the quality of insulating material degrades. Alright. So, if you see this will create what? It will create path for electrons that can flow through that. So, room temperature silicon in air creates a native oxide. We have seen that example also, which is poor insulator and can impede the surface processing. That is why what we have to do, if before we start using the silicon wafer, we have to dip the silicon wafer in BHF, buffer hydrofluoric acid. This is buffer, BUFFER, buffer hydrofluoric acid. Okay. And if you want to understand how the volume expansion occurs, then this is the formula. So, there are three types of oxidation technique. One is dry oxidation, another is wet oxidation, another is cryogenic oxidation. Now, you will again ask why we have to learn silicon and oxygen and oxidation and other techniques. The reason is that we will form a chip, right, that is coated with an metallic layer, and the base can be silicon. But if I deposit, this is the top view, if I deposit, and this is a cross sectional view, if I deposit metal on silicon, then it is a short, right, because silicon is semiconductor. That is why what I will do is, so this is a metal, you understand, this checks are metal. So, what I have to do is I have to form silicon dioxide, and on silicon dioxide I have to deposit metal, right. So, this is my metallic layer, this is silicon dioxide, and this one base material is silicon. So, if I show you that okay, you use this chip for EEG measurement or for other measurements, you will ask a question, what exactly is the substrate? We say silicon. Then the question is how silicon is fabricated. That is why we took the class on silicon fabrication. The next question is if I want to have insulating material between silicon and metal, what kind of insulating material I can use. So, we are discussing silicon dioxide and its growth process. Okay. So, everything that I will be covering as a part of this particular module, and the remaining modules are related to the EEG electrode design as well as the fabrication techniques that will be used for understanding some of the properties of the brain. Alright, and that is why it is very important to understand all these details before we actually go into the application part. So, coming back to your thermal oxidation, like I said, if the first one, which is dry oxidation, in this you have oxygen and you have nitrogen. Now, what is the role of nitrogen? You see, what you see here is a furnace. Furnace, what is the temperature? We have seen it should be 900 degrees centigrade and 1100 degrees centigrade. This should be temperature anywhere between 900 and 1100 degrees centigrade. So, if I heat the furnace at 900 or between 900 and 1100 degrees centigrade, and this lines that you see like this, you see here, this one, these are silicon wafer. So, I have this like this, okay, silicon wafer in a slot, it is holding this silicon wafer, and this whole thing is within the furnace. Okay, very bad drawing, like this. Okay. This is a horizontal tube furnace, you can see the tube is in horizontal direction, right, horizontal tube furnace, these are silicon wafers. Alright. Now, this temperature is 1000 degrees centigrade, let us assume that the temperature is 1000 degrees centigrade. If I start oxygen, right, while the furnace is heating, then you will not get an optimized silicon dioxide on this particular wafers. So, what is the role of nitrogen? Initially when you are heating up the furnace from room temperature, let us say 25 degrees centigrade to 1000 degrees centigrade, right, you need to make sure that there is no silicon dioxide that is growing on silicon wafer, and that is why what we will do is we will close the oxygen supply and we will only have nitrogen gas into the furnace. So, if we purge nitrogen gas inside the furnace, then nitrogen being inert gas, everything is N2, right. There is no silicon dioxide on the silicon wafer that are inside the furnace while the furnace is heating on. Okay. So, initially nitrogen is purged in the furnace, and once the furnace temperature is achieved, then nitrogen is switched off and oxygen is switched on. In that case, what will happen? Oxygen will start reacting with silicon to form silicon dioxide, right. Now, let us understand what happens when it is wet oxidation. In wet oxidation, you have a heating module and you have something called bubbler, all right, inside which you can have water, and when the water heats up, there is a water vapor that is created. Initially, again what you will do, you will close this valve, open this valve, open the nitrogen valve and close oxygen valve when the furnace is ramping up from 25 to 1000 degrees centigrade. Once the temperature of the furnace is 1000 degrees centigrade, once we achieve this temperature, then what we will do? So, initially only nitrogen is allowed to flow inside the furnace. You can see that if I open the nitrogen valve, and if this valve here is opened, then the nitrogen can pass through furnace. So, initially when it is ramping up, we will open nitrogen. Once we receive the once we get the, or once the furnace is at 1000 degrees centigrade, then we will switch off the nitrogen. Okay. We will switch on the oxygen valve, or we open the oxygen valve, we will open this valve, we will open this valve and we will close this valve. So, what will happen? Oxygen will pass through the bubbler and it will take the water vapor, and this water vapor will pass into the furnace. That means, H2O in gaseous form will pass to the furnace, and silicon will react with the H2O in a gaseous form, which is water vapor, to form silicon dioxide and 2H2, which is hydrogen gas, which can come out of this particular furnace. So, this is how the wet oxidation is done. The final one, which is the cryogenic oxidation. In this case, what we do? Again, initially you have only nitrogen open, H2 is closed, O2 is closed. Once that furnace achieves or reaches the required temperature, our example is 1000 degrees centigrade, we stop the nitrogen valve and we open H2 and O2 valve, so that H2O, when H2 reacts with O2, it forms H2O, and that H2O goes inside the furnace or purges inside the furnace to form the H2O2. Wet oxidation using H2 and O2 is more popular or cleaner than H2O. So, if you want to use wet oxidation, then it is better you go for cryogenic oxidation, since you have a cleaner H2 and O2 rather than using the water and using the water vapor by heating metal and then carrying these with the help of oxygen vapor. So, these are three techniques that are there with us for the silicon dioxide growth, and if you see how the horizontal tube furnace looks like, you can see from this particular figure that there are three tube horizontal furnace, and then there is a vertical furnace, while vertical furnace is not that popular compared to the horizontal tube furnace. This is one, this is second, this is third, this is here you can see that there is a tube, right, which can be heated at a high temperature. And let us see the next slide, so that we can understand better. You can see here that the silicon wafers are being loaded inside the furnace, right, and here you can see that the engineer is loading the wafer using a silicon rod, all right, is called silicon carbide rod, not silicon rod, silicon carbide rod. Alright. So, this wafer is pushed inside the furnace, not directly touching the wafer holder, but by using the silicon carbide rod. So, what you have here is this the tube that is used in horizontal tube furnace is made up of quartz, and you have a silicon rod to push the wafers inside. There are heating coils, and it's heated by resistance. Oxygen or water vapor flows through the reactors and pass the silicon wafer, and the typical velocity is order of around 1 centimeter per second. So, the steps would be wafers pushed in the nitrogen gas flow, oxidation process at 900 degree centigrade to 1100 degree centigrade with the flow of oxygen or water vapor with nitrogen carrier gas. Wafers are taken out with the nitrogen flow. This is how the generally the ramping is done, and slowly and actually not ramping is done. This is the where the temperature is maximum is in the center of the wafer. If the wafer is of the furnace, if the furnace is around 40 centimeter 45 centimeter in length, you will see that close to 15 and 25 you have the kind of an optimum temperature achieved. So, this is where the wafers should be placed. This is a photograph of a silicon wafer and silicon dioxide wafer. Like I promised in the last class that I will also show it to you how the silicon wafer looks like. If you see my hand, you will be able to see this is the silicon wafer that is I am holding in my hand. Okay. If I am just rotating or tilting little bit, you will be able to see a grayish color, right, a grayish color. But if I have a silicon dioxide, I will show it to you. So, to compare, you will see here that the color is about purplish color, right. So, you have a purplish color compared to the grayish color. You can see here I am tilting both the wafers so that you understand. You see here, right, this one is gray in color, this one is bluish or purplish in color, right, this one is purplish in color. Why? Because this is silicon wafer without oxide and this one is silicon wafer with oxide, alright. Now, let us see what is the back side of this wafer. We also learned about single side polished and double side polished wafer, right. This one is single side polished. You can see the image of the let us say hand or a finger on the silicon wafer. Can you see that? You see, I will show it to you. You can see the reflection, right, reflection very clearly. You can see the reflection. You can see let us say if I put my finger here, you are able to see the finger also coming the image of the finger, right. But if I show you the back side, you see nothing, right, this is rough area. So, a surface from which the front side is polished and the back side is rough, it is single side polished wafer, it is single side polished wafer. You may get wafer which is double side polished, which are mirror surface on both the sides, but this wafer that I am holding is single side polished wafer, right. This is rough surface, the front surface is a smooth surface. Now, let me also tell you that the way I was holding a wafer is not correct. We cannot use bare hand to hold the wafers. We must use tweezer, we must use gloves and then only hold the wafer. This is only for demonstration purpose, that is why I was holding with my hand. Also, we have discussed that other than silicon we can also use glass, is not it. So, this is a glass wafer, you can see it is transparent, right, it is a glass wafer, but it is a wafer, right, it is a whole circular wafer. And what will be the thickness? Disappears, right. What is the thickness? The thickness is close to 500 microns. 500 microns thick is a whole silicon or silicon dioxide wafer or glass wafer, right. On this glass wafer we have patterned certain things, do not worry about this pattern right now. The point that I was making is you can also use a glass wafer instead of your silicon wafer, right, this is a glass wafer. So, depending on the application you can change the substrate, these are substrates, and if you see the screen again, then what you will see is that this one is your silicon and this one is your silicon dioxide. When you grow silicon dioxide, this is silicon dioxide on silicon wafer, okay, and this is just silicon wafer. So, when you grow silicon dioxide on silicon wafer, since silicon dioxide is transparent, you will be able to see the change in the color of the wafer depending on the thickness of silicon dioxide. So, there are two ways to understand what is the thickness of silicon dioxide. One method is called surface profilometry, which is a mechanical measurement. And how does it work? So, in this case I have a silicon wafer and I have silicon dioxide grown on silicon wafer. Deliberately I will leave this space, I will not grow silicon dioxide in this area. Okay. And what I will then do is that, or let us say in another way, if I have silicon dioxide everywhere like this, and I want to know what is the thickness of this silicon dioxide, right, that is a question. Then in that case I will perform a photolithography and etch silicon dioxide only in this area, where other area silicon dioxide still is there, and then I will use a stylus. You can see here, right, you can see here I will use a stylus. Stylus is a diamond tip, with a diamond tip, and this diamond tip I will scan it in this direction. So, it will come here, then it will come here. So, when this happens, what will happen? There is a step that is created. Let me again tell you, let me draw it little bit on this side, so it is easier. I have a silicon wafer, oxidized wafer. I am patterning the silicon dioxide using photolithography, and then I am using a stylus to move across the silicon or scan this silicon wafer. What will happen when it scans silicon wafer from this end to this end? There is a creation of step, and this step will tell us what is the thickness of the oxide on the silicon wafer. So, same is shown with the in the schematic. You can see here there is a travelling stage, there is a stylus, there is a scanning line, and it moves across the wafer, and it will tell you the step or the size or the height of the silicon dioxide on the silicon wafer. All right. So, the disadvantage of this particular method is that this is silicon dioxide, right, and I have, let us say 25 wafers. So, one wafer I have to sacrifice, because in one wafer I have to remove silicon dioxide from a certain space, and that is why this is a destructive type of technique. What is called destructive? Because it will destruct the silicon dioxide on the silicon wafer, and that is why we left with over 24 wafers, right, because I have to remove silicon dioxide from silicon to understand the thickness of the silicon dioxide. All right. So, when you see this kind of systems, it will help you to understand what is a thickness of the silicon. This also is called alpha step profilometer. It is also using the similar technique which is used in atomic force microscopy. So, there are multiple ways of using the similar kind of application to understand the roughness of the film. Second idea is that, so if you see the screen, if I have the wafer, right, I am drawing a wafer on the screen, right, and if the silicon dioxide as I am growing is uneven like that, okay, how would I know what is the roughness of this silicon dioxide? This is silicon dioxide. So, to understand the roughness of the film, I will scan this film again with a stylus profilometer, and I will understand what is the roughness of the film. All right. So, this can be used for many applications. Now, the second way is by observation. This is a crude way of determining what is the thickness of silicon dioxide. As you can see that the relative illumination intensity would change depending on the thickness of the film. If we have a film which is about 100 nanometer, then the reflection would be like this, compared to a film which is 900 nanometer or 1000 nanometer, which will look like dark green. So, it is very important to understand the silicon dioxide thickness, and this is an extremely crude method to understand what is silicon dioxide thickness. The right way is either use the alpha step profilometer, which is your stylus monitoring, or you use the another way, which is called the ellipsometer. But before we go to ellipsometer, let us see that the thickness determined by observation, right from 500 angstrom all the way to 9900 angstrom, we can see that how the color changes. And if we talk about alpha ellipsometry, then you can see here that it will help to understand the thickness of the film without destructing the film, because it is based on the reflection of the light source from the substrate onto the detector, right, and there are several stages inside the ellipsometer, right from filter to polarizer to quarter wave plate, analyzer and detector. And after quarter wave plate, the linear, so when you incident the light, then after this quarter wave plate, the linear polarized light becomes circularly polarized, which is incident onto the oxide cover wafer, which is this one. The polarization of the reflected light, which depends on the thickness and refractive index of the oxide layer, is determined to use to calculate the oxide thickness. And finally, multiple wavelengths or incident angles can be used to measure the thickness of the each film. The only disadvantage here is that some of the metal films cannot be the thickness cannot be determined. Okay, so that was the end of this particular module. In the next module, we will see how photolithography can be used. Photolithography is a heart of microfabrication technique, and if you learn photolithography, then you can design not only sensors, not only transducers, not only MOSFETs, but lot of other applications or lot of other devices as well, whether it is biomedical application, whether it is microelectronics application, or it is just pure mechanical engineering application where you want to determine or design and fabricate an actuator. You can use microfabrication or photolithography technique. So, we will see this technique in the next module. Till then, you understand the importance of silicon dioxide on silicon wafer. If you have any questions, you can always ask in the forum, right. Dr. Mahesh will help you out to understand all the questions. So, we also have and we will all help you out to understand what are the possible solutions to your questions, if any. Right. Till then, you take care, and I will see you in next module.